Hey guys, Mr. Betts here. I want to talk more about alternating series and more specifically how we can find the sum or at least approximate the sum of an alternating series. If you remember, for the most part, our main question is whether a series converges or diverges. But there are some special series that we can actually find the sum, like a geometric series, or we can at least bound the error of the sum so we can figure out how far off an approximation of the sum is, and that's going to be the case for the alternating series. So let's just refresh real quick what the alternating series test says. And the alternating series test essentially says that if a series is an alternating series, the terms are decreasing in magnitude and the terms are approaching zero, then the series is going to converge. And if you remember when we talked about the alternating series originally, there were some characteristics of the partial sums that really forced the series to converge based on those three conditions. So this was an example that I used in that video where we introduced an alternating series and why it converges. And if we look at the partial sums graphed on the graph below and how that compares to the infinite sum, and since this is a geometric series, we actually know the infinite sum is going to be 2/3. We can see that every other partial sum is too big and every other partial sum is too small. And also, the partial sums themselves are getting closer and closer and closer to the actual sum. And that's what we should expect in any series that converges. But because of those characteristics of an alternating series, then we know that not only does the series converge, but it converges in a very particular way. So I highlighted here the even partial sums and the odd partial sums, and you can look at this on the graph, or you can look at the numbers, and you can see here that the even partial sums are all a little bit bigger than 2/3, and the odd partial sums are a little bit smaller than 2/3. But every other one gets a little bit closer and a little bit closer. So the even ones are decreasing, the odd ones are increasing, and they're squeezing that actual sum in between the partial sums. So some things we know about an alternating series, and then conclusions that we can make. And again, these are things that we talked about already. So to use the alternating series test, the terms have to decrease in magnitude to zero, and the terms have to alternate. Because of those two things, the alternating partial sums, so every other partial sum is going to be an over approximation. So all the green ones are over approximations, all the red ones are under approximations. The over approximations are getting smaller, the under approximations are getting bigger, and since the terms are getting smaller and smaller and smaller and closer to zero, this is kind of the big idea that's going to let us figure out errors here. Each partial sum jumps past. Okay, so I'm kind of using this informally, but notice that each partial sum crosses over the actual sum, and it jumps past by a smaller and smaller amount each time. And this is the key to the alternating series error bound. So the alternating series error bound says that the difference between the nth partial sum and the actual sum, so remember S is just the sum of infinitely many terms added together, is going to be less than the magnitude of the next term. Okay, so this is the sum of the first n terms, this is the n plus first term, and that n plus first term is going to give us what's called an error bound. So this right here is the mathematical way we would write that. So the difference between the actual sum and the partial sum, that's the error. That's how far off the partial sum is. And that's always going to be less than the magnitude of the next term. Okay. Not only that, but we know that if the last term we added on was positive, then the partial sum that we're dealing with is going to be a little bit too big. Because every time when we add a term or we subtract a term, we're jumping past it. So when we add a term, we're a little bit too big. If we add a negative term, then we're going to be a little bit too small. So not only do we know a bound on the error given by the n plus first term, so magnitude of the bound, we also know if it's going to be a little bit too big or a little bit too small. We could alternatively think about this. Instead of saying the nth term is positive, we could also say the n plus first term is negative. So if the next term is negative, that means the approximation that we're dealing with is a little bit too big. So it's an over approximation. And the reason we might think of it this way instead of as the nth term is because the n plus first term is the one that we're calling the error bound. Just a note, the difference right here, the absolute value of the difference is called the error. So again, that's how far off we are. It's also sometimes referred to as the remainder. And the reason we call it a remainder is because it's what we get. It's the quantity of the rest of the terms added together. So if we add the first 10 terms together, that's going to give us a partial sum. All the rest of the terms are the remainder, and that's how far off we are.